Welcome, ladies and gentlemen. My name is Diego Rovetta. I'm the chairman of the EAGE Local Chapter in the Netherlands, and I welcome you to this first event for 2022 of our chapter. The topic is very exciting. It's going to be related to quantum computing in geoscience. And before starting, I will just introduce the talks with the usual welcome to all the EAGE community that is with us this afternoon. I also have some announcements about the board committee members. And then I will go through today's agenda, some basic house rules for this event. And then, of course, I will introduce the speakers. So let's start as usual. I welcome all the EAGE community, in particular our friends from the local chapters of London, Paris, Oslo, Aberdeen, and Germany, that are the ones that we are more in close contact with. But also, I would like to welcome, as usual, the student chapters of DOGS, Delft, and Aachen, as well as the Oslo Society of Exploration Geophysicists. As you well know, we have our page on LinkedIn, where you can find us, find the events that we are organizing. And if you want to contact us, you can do it through the LinkedIn page, as well as by email. The email of our chapter is eaglcnetherlands@gmail.com. Let me first start with the board committee member for 2022. I already talked about the new board in the event in December, but we had a couple of changes. So we have two newcomers. One is Dong Zhang, that is serving as event assistant, and the other one is Yonno van Liesendik, who is our students coordinator. There is also one person that is missing, is Dorit Könitz, that left the board, and for that I have a special slide after this. So let me welcome Dong and Yonno. Dong is from TU Delft. He's living in Den Haag. He has a background in geophysics, more specifically seismic signal processing and imaging. He's a PhD candidate in the computational imaging group of the Faculty of Applied Science. Yonno was born 27 years ago in Limburg, currently in his final year of PhD at TU Delft. He's working with Kees Vapenaar on time-lapse application with the Marchenko method. And in his free time, he enjoys squash, bouldering, and chess. So welcome, Dong, and welcome, Yonno. And finally, we have a living member, as I mentioned before, Dorit Könitz. She moved back to Germany in December, so she thinks it's not feasible to continue to serve on the board, even though she will continue following us online when we have a virtual event. She said, it was very nice to work together with all of you. The highlight was to win the EAGE Local Chapter Award, and I wish you all the best for the future. I'm sure you will organize lots of exciting events and activities. And of course, we thank you, Dorit, for your service. And of course, we wish you all the best for your personal and professional life. Now let's go to today's agenda. After this brief introduction, there will be the technical talks entitled Quantum Computing Opportunities in Geoscience and Some Early Applications by Professor Matthias Möller from TU Delft and by Dr. Marcin Dukalski from Aramco. After their talks, there will be a Q&A and discussion session. As usual, during the talks, you can start writing your question for the speaker in the chat box, clicking the dots there and then the chat option. And then at the end of the meeting, Florencia will read the questions for you, for the speakers, but we will also unmute you so that you can interact directly with the audience and with the speakers as well. So now let me introduce the speakers. The first one is Matthias Möller, is Associate Professor at the Department of Applied Mathematics at TU Delft. He obtained a diploma in mathematics from the Faculty of Mathematics at TU Dortmund University, Germany in 2003, and a PhD from the same institution in 2008. He joined the numerical analysis group at TU Delft in 2013, and his research interests focus on numerical methods for partial differential equations and their efficient implementation on heterogeneous high-performance computing platforms. He has been working on high-resolution adaptive finite element and isogeometric methods and fast iterative solution techniques, in particular for convection-dominated transport problems and compressible flows. Since recently, Matthias is working in the field of quantum accelerated scientific computing with focus on quantum algorithms for numerical linear algebra and optimization problems. The second guest speaker is Marcin Dukalski. He joined the Aramco Delft Global Research Center as a senior scientist in 2018. Prior to that, he worked at the Shell Research Center in Rijswijk and in Amsterdam. His work is focused on seismic data processing, in particular multiple attenuation, as well as potential applications of quantum computing in geophysics. Marcin got his PhD from the Kavli Institute for Nanoscience at the TU Delft in 2013, where he worked on theory and experiment of quantum entanglement and decoherence. Since 2019, Marcin has been an industrial advisor to the Dutch National Agenda for Quantum Technology, which aims to develop the economic sector of quantum technologies in the Netherlands. So thank you to the speakers for joining us tonight. I will make now Marcin presenter, and the stage is yours.
Thank you very much, Diego, for this very nice introduction. So my name is Matthias Möller, and I'm very happy to talk to you together with my collaborator Marcin Dukalski on a very excited hot topic, quantum computing, and give you some insight into which opportunities are there for geoscience in specific, and show you or share with you some early applications. Let me also introduce co-workers which have made this presentation or these results that we are showing in the second part of the talk possible. So that is Professor Frank Philipsen and Niels Neumann from TNO here in Delft. That is Diego and Marcin from Aramco, and a master student that we all supervise together, Stan van der Linde, here in Delft, who produced the results that we show at the end of this, or at the second part of this talk. So, as you all know, I guess, that all the computations that we do are very complicated and are typically very time consuming. And we are very often in this dilemma. If we want to have a good solution, then we have to wait. If we want to have it fast, then it's not a good quality. So then it's very, very low quality. And the same with a cheap solution, then it's also low quality. What we actually want to do is a good, a fast, and a cheap solution. So this unicorn in the middle. Yeah. And while we are often chasing after this, say, very ideal unicorn, there's a, let's say, first order approximation of this. Yeah, that's what we get. Yeah, so the question is, why is it so difficult to get and chase this, say, ideal unicorn? And that is where we have to look at what plays into the computations that we are doing. Yeah, because it's, of course, the algorithm side that have to interact or that have to work nicely together with the data and with the compute infrastructure, so the high performance computing infrastructure. And you see here, it's this very tiny area in the middle where, yeah, if everything comes together in an optimal way, where we have a chance to find the ideal unicorn. Yeah, so we are not talking about data today, we are talking about algorithms and high performance computing. And let's start with a second. Let's start with high performance computing. Yeah, so classically, it was easy to get more performance out of classical processors. Yeah, so this is Intel's very well-known tick-tock model. Basically, every year or every few years, there was an improvement. There was either an improvement in terms of the microarchitecture, that would be the flat stairs. Yeah, basically, you can translate it to the technology has been improved. There have been new comments in the processor, new features. And then this feature map was frozen and the fabrication size was reduced. Yeah, that means you could put more transistors on the same size. And this tick-tock model went on until about 2014. And then you see there is a kind of plateau. Yeah, so from these 14 nanometers fabrication, it takes quite some time, 4 years roundabout. And then there is a small shrink to 10 nanometer. And well, there are some processors already below 10 nanometer. But the problem is we are reaching some physical limits. Yeah, so Homer is quite right in saying the end is near. We are really running against physical boundaries. And that is not something we can, by some smart thinking, circumvent. It is really, inherent to the traditional classical compute technology. So what we need is really a new thing if we don't want to accept that the end is near. And this new thing could be, and we strongly believe it is, quantum computing. And so when you hear about quantum computing, you might have heard about maybe the most famous one, so the factorization algorithm, which is basically saying with a quantum computer, we can factor a large integer number very efficiently. Well, is that interesting? It is, because this whole concept is underlying many of today's encryption schemes. Yeah, so if you're sending some message in an encrypted way over the internet and don't want others to read it, then RSA, for example, or other encryption schemes are based on the fact that a classical computer would need years, tens, hundreds, thousands of years to break this encryption. And the problem is a quantum computer has a completely different scaling. So you see this very flat and slowly growing slope. Yeah. So for a quantum computer, it doesn't make too much difference if we have 1,000 or 10,000 bits. It is still a question of seconds to break that. And so in this case, the quantum computer would be the bad guy because it destroys the security that we have right now. But quantum mechanics can also be on the good side. So there is something called the quantum key distribution, which is a quantumish version of encryption that is unbreakable. And this is not just a fancy thought construct, but this is really, as we speak, so in this week of February, is really in operation at the film festival in Berlin, the Berlinale. And their quantum key distribution is used to, say, exchange the movies in a safe way, so that no one can steal them. Yeah, okay. So, but these are not, say, breaking encryption and assuring a new way of encryption are not the only applications. There are many more use cases. And according to this McKinsey report from 2020, it is the global energy and materials sector which is on position 2, right after finance, which is maybe one of the most obvious industry sectors. And the interesting thing is it is not just in the long term, so long term would be somewhere 2035, but it's really in the medium and even near term. That means as we speak in the coming years, it has quite some potential to add value to this industry sector if we use some type of quantum computing technology. Next slide, please. Yeah, and this is something that not just academia has recognized, but also the governments worldwide. So it's basically like a race to the moon. Yeah, so all nations are investing massively in quantum computing. These are just the numbers of public funding. So that's why the United States seem to be on position 3. They do a lot with private funding as well. And if we zoom into Europe, we see that the Netherlands has quite a significant share on this. Yeah, so some around about 12% of the whole public funding in Europe is done by the Netherlands. And just recently, there was a very huge first initiative. So you might have heard about the quantum delta and L that has been awarded some more than 600 million euro with the idea to really build up some quantum technology environment. Yeah, so what this quantum delta and L actually is, it's say a foundation with say places or hubs in 5 different cities. And you see on the map on the right, it really comprises the software development, the hardware development, technology development, and it's really the right place to be if you want to do something in the field of quantum computing. Yeah, and that this, say, governmental investment can become a big success story. We have seen some years ago, ASML, so nowadays the world's leading manufacturer of chip printing machines, yeah, it also started as a spin-off of academia with a lot of public investment. Next slide, please. Well, maybe you might have heard about quantum computing or read something about it or watched some YouTube video. And what you very often see, I would call it the traditional quantum computing, is something like this. Yeah, so you see a schematic illustration of how the quantum algorithm would work. This is, for example, the one to solve a linear system of equations, but you do not recognize the A, the X, the B that you typically want to solve. Yeah, so it's very abstract. If you then look at how this is built in real hardware, it looks like that. Yeah, very different. The only thing that you might recognize is C knots and these red beams. Yeah, so this is, by the way, a photonic implementation. These red beams are kind of, yeah, can be associated with the horizontal lines in the schematic picture on the left. Yeah, so when you then leave the experimental implementation and look at the majority of publications, you will see tables like the following. Yeah, and that is overfull of complexity results, which in very detailed way tell you how complex, how expensive, which part of the whole algorithm is. And I don't want you to understand all these details. It's just to show it's very theoretical and very, say, far away from practice. Then there are a few publications where things have been implemented. Yeah, typically they are implemented in a simulator, and then the brave ones step to a real quantum computer and figure out, yeah, if I can read this quote, on the other hand, due to the imperfection and noise in a real quantum computer, the hardware execution of the same circuit, so the same circuit is one that was very successfully run on a simulator, does not give satisfactory results. And you might ask, was this now a super complicated problem? Yeah, something that we couldn't solve on a real on a standard computer? No, it was this one. Yeah, a 2x2 system which you can solve with pen and paper or even in your head. And this was not solvable on a real quantum computer. When I say real quantum computer, I should be a little bit more specific because there are 2 distinct types of quantum computing. There's on the left-hand side, the gate or circuit-based model. That is, say, you can associate it with this abstract figure we had on the previous slide. Yeah, so they are still quite immature. We have around 100 qubits. We have a TRL level of 4 to 5. And what is even more frightening is we have very few use cases and algorithms. Yeah, one can play around with them. It's very interesting because they're universal. They can solve many different problems, but we are not yet there that we can solve these problems because we don't know which ones we can solve, how we can write the algorithms. And then on the other side, there is a technique called quantum annealing. Yeah, that is not so universal. It's very task specific. It can solve one problem, namely optimization, but that it can solve very well. You see the number of qubits is about 5,000. Yeah, so much more than the hundreds from the universal ones. And the TRL level is also much higher. And what is for people who are interested in applications particularly interesting, there are many, many use cases if we stick to the field of optimization. So that's the outline of the talk. And the first part will be about exactly this, about optimization. And when we look at what students do, what all of us do, if there's a corner on the way, you simply ignore this corner and you take a shortest path, yeah, a least path. So you are intuitively optimizing your way, whether that's good or not. And if the gardener wants that, that's another question, but you naturally optimize. Yeah, so and this idea of a least path optimization problem, we find in many different applications. We find it, for example, in seismic imaging, where shooting some waves and seeing them being reflected and measuring them, we can recover some properties of the ground. Yeah, and this all follows the least or shortest path optimization principle. Also, when we move to rivers, yeah, so the deltas where water is flowing, nature naturally seeks the way or finds the way of least resistance. Yeah, so it will not go through a rock if it can go, say, around it, and there's some soft material. And you can say this kind of water in the deltas, in the river deltas, is a continuous optimization problem that goes on every day. Yeah. Also, if we leave the surface and go to subsurface flows, yeah, so liquid in the subsurfaces also follow the same principle. And yeah, and when we are actively doing something, so drilling into the ground, for example, we of course also want to find the way of least resistance. Yeah, so we're also seeking for a least path optimization problem. Speaking of this, there are, you see on the left, many different areas or types of optimization problems. Yeah, so many scientific or inverse problems in material science, in chemistry. And the thing that is particularly interesting is deep learning. Yeah, so a very, very hot topic in science too. And what makes deep learning possible is that we have very good optimizers. Yeah, because deep learning very heavily is built on the fact that we can optimize these weights in these networks. Yeah, and you see two other maybe more practical applications in logistics and logistic networks on the water and also on the land. And the key that we have in these problems, very often the interesting problems are very hard to solve. Yeah, so I'm now referring to the NP-hard class of problems, whereas the class that is easy to solve, that would be P, is very often kind of boring or not so attractive. And an idea, and that is also underlying a little bit the approach we are presenting here, is if you can't solve the problem you start with, maybe you can transform it into a problem that you can. Yeah, so step by step, you transform it into a, not simpler, but simpler to solve problem. And then once you have done that, you can also solve your originally hard problem. Next slide, please. Let me illustrate it with a very, simple example, the paint shop problem. So this is something from Volkswagen. The problem is simple. You have cars manufactured and you want to paint them. Yeah, so let's assume for simplicity, we have a couple of cars and you can only order two colors, blue and red. And if you would just randomly color them, this would mean here you have to change from blue to red, then to blue again, to red, to blue, to red. And this changing, that costs, of course, time, because it's, you have to change the nozzle, you have to clean it. And at the end of the day, you can process less cars. You can also translate this to every 1.4 cars, you have to switch the nozzle. So if we would optimize this process chain and just, turn around the order of the red and the blue car, then there would be exactly one change from blue to red after having processed 4 blue cars. And then the ratio between cars and switches and changes is much better. Yeah, so from 1.4 we come to 7. And that of course means we can paint more cars per day, which at the end means we can make more money per day. So this was just an illustration. Here's really some original data from Volkswagen. They also made a simplified model. They had two colors, so black and white. Yeah, so on top you see the original, say, random input value. And if you use the standard methods, so so-called greedy methods, you get a, say, switch between white and black like this. Yeah, so on average, every 5 cars, you have to do a switch. They also did it with a quantum approach, and you see it is more than a factor 2 more efficient. So now we can paint round about 13 cars before we have to switch. And that, of course, means a huge saving in the production time or a higher throughput per day. So let's dive one level lower into the mathematics of these optimization problems. Yeah, so here on the left, we see a parabola, and I guess it's very easy to see where the minimum of this function is. Well, it's of course at the bottom, and the mathematical description of this would just be a polynomial of order 2. Wow, we all learned at high school that this problem has a very simple analytical solution. Yeah, so the position x min is just depending on the b and a parameters. We can write it down. We don't have to think about it anymore. But what if we make the problem slightly more complicated? Yeah, we still leave it as polynomials, but now we say a polynomial of order n. So how does this polynomial look like? Well, it can be quadratic, it can be cubic, it can be quintic. And the funny thing is that for n larger than 5, there is no formula that we can write down. And it's not because we are too lazy or don't invest enough time to write this down and find this formula. No, it's really a mathematical law that does not exist such a formula. Yeah, so no closed form expression. And that is only if we have one variable. Yeah, so if we would have more variables, it would be even more complicated. Yeah, and well, Marcin, you went quite quickly through this. If we think about the shape, yeah, so how would such a problem look like? Yeah, it can look like this or that. And you see there are very fine scale features. Yeah, for example, here we see the optimum, so the minimum is at this very small down pointing peak. Yeah, and if we want to optimize that, that means if we want to find this peak, that's quite difficult. So how can we find this peak? Well, the brute force approach would just be sampling. Yeah, so let's assume the red curve is the graph or the shape of our polynomial that we want, from which we want to find the minimal value. We don't know, so we do not have this graph. Yeah, we just have the formula, and we can have a lot of balls like samples and let them fall and try to sample what is the position of, say, what's the position of this curve. And if we are unlucky, we get a sampling profile of this. Yeah, and then we have absolutely no idea about the real shape. Yeah, so it looks like there are two flat regions which are connected at some point, but we completely miss the important information that there is a local minimum somewhere. Well, we have to do some smarter sampling. How could we do that? Well, we could let this ball fall and then find a local minimum. Well, that works here, but we still have not found the global optimum, the global minimum. Well, if we throw this ball again, it might get stuck in the next minimum. Well, we might have hope that it somehow finds the right one, but maybe if we are unlucky, it doesn't. Yeah, so we are hopping back and forth between two local but not global minima. And if we throw a lot of balls, well, we still might be unlucky that we are finding a lot of local minima, but not the global one. And of course, if we do that with many, many balls, that's very compute intensive. Yeah, so that's not an approach that is feasible for real problems. So, and just to connect back to the Volkswagen example, finding one local optimum versus finding the global optimum, yeah, that can be the difference between painting 5 cars before we have to switch the painting nozzle versus 13 cars. Yeah, so it's really important that we find the global and not just a local optimum. Could you go forward? Yeah. So what would be nice to have is if we are somewhere in a local optimum that we magically know where to go into the global one. Yeah. So that's what we would like to achieve. And the question is, can we achieve that? And I hope we can convince you that with quantum computing, we are able to do that. So, and this is the point where Marcin is taking over.
Yes. Can you hear me okay?
Yes.
Excellent. All right. So the process in the last slide that Matthias just discussed is exactly what this chip is trying to emulate. And we'll get to the bottom of how this works exactly, but in principle, there is already a device built to do that for you. What it effectively does is, instead of the what we would call thermal jumps or thermal annealing sort of type of algorithms, it physically is allowed to use the process of quantum tunneling to get from one local minimum to some neighboring local minimum, which is lower than one it started off with. To sort of understand where this comes from, we have to make this your typical distinction between bits and qubits, and perhaps you've heard the story 1,000 times. I'm trying to put a slightly different twist on it for purposes of what we're going to discuss later. So don't zone out just yet. Bits, you can think of it as a coin. It's either heads or tails. And then qubits, you can think of it in terms of a coin that is mid-flight. It is one or the other unless you actually catch it, right? That's why we toss the coin. You can also think of a qubit as a little bit of a magnet. That thing can either point in a north-south direction or a west-east direction, or anything in between, and it is allowed to rotate, right? Now, the nice thing about this analogy to magnets, and what makes qubits distinctively different from bits, is that if you have 2 coins, that gives you 4 possible outcomes. But if you have 2 qubits, and if those qubits interact with each other, that's the important bit, much like 2 magnets can interact with each other, those qubits could become correlated, okay? Such that you no longer have 4 possible outcomes, but you just end up with only 2, all right? And what happens when you put a number of those magnets or compasses all together, they form a somewhat of a mathematically complex to describe system, which we will later call an Ising model, right? All of those low magnetic needles indeed interact with the Earth's magnetic field, but they also have influence on each other. And depending on how strong a particular magnet is, how close it is to its neighbor, you will have a very different system that is interacting. So let's abstract those magnets away to those little balls with an arrow pointing upwards for north and downwards for south. And we can describe that different magnets have different amount of influence on each other by the thicknesses of the green lines, and how difficult or easy it is to change a particular magnet's direction by some meaning of like inertia, which we'll try to describe by the size of the ball that is it. So if I flip back and forth, you can see that we are talking now about 2 different systems. And it so happens that the objective function, or the energy distribution of the system, depending on which of those balls, which of those magnets, compasses, points north or south, up or down, is given by some very, very complicated function, right? And if we start with every single magnet being pointing in a certain direction, then that might not be energetically most favorable orientation. And now if we let quantum mechanics do its work, what happens is that this system by itself, by the laws of physics, will relax into the possibly lowest energy state. So that's why people don't tend to talk about this in terms of this is a computer, that you actually have a computer do the work, but it's you would call it a quantum annealer because it's a process of settling into the ground state. And so instead of performing a set of operations or doing math on a computer, we actually change and we actually map an optimization problem that we wish to solve onto an actual physical optimization problem that is happening before our eyes, except it's a problem that can benefit from quantum tunneling. So this is exactly what Matthias was referring to earlier when he said, hey, you know, if I can solve one of those models, and if I can hop between, or problems, if I can hop between different kinds of problems, then I can also work my way backwards. What if I have a problem that is here in the bottom left corner, that dot, and I can transform it into a problem that is described by an Ising model. And if I have a machine that is an Ising model simulator, then I can use that to find solutions. So how does it work in practice? To do that, I really want to go back to the classical side of things for you to really appreciate how different this is. So you're going to start with some kind of a problem. You say, okay, I have a problem that I have to solve. And typically what helps accomplishing this task is that you start writing down some mathematics, right? That's why we learn mathematics. We do that to solve problems. Conventionally, you would then maybe try to write some pseudocode and some if-then loops, some more complicated things. That could then give rise to you writing a computer program. A computer program would be then compiled into a machine code. A machine code gives very specific instructions to electrons as they are supposed to move through the circuitry, right? The very circuitry that we are hitting a hard limit on the 10 nanometer processors. On the quantum side of things, this is very different. We still start with a mathematical formulation, but then we map it onto the Ising formulation. We take an optimization problem and we try to rewrite it as a different optimization problem. But that's not enough, because then we have to take this optimization problem and we have to abstract away some quantities from it. So from that grid that you see, from those thicknesses of the different bars, the sizes of those different circles, I can put it as the numbers on the vertices and the numbers on the inside, on the edges, and the numbers on the vertices, respectively, to represent the same information. But this quantum annealer doesn't solve every single possible problem, because it's just a machine that's built to solve as many of them as possible. So you have to have a translation that goes in between. So we have the hardware graph, which basically tells you about how the individual compasses or qubits are connected on in the computer, and then you have to figure out how to describe your variables in terms of the variables that are present on the computer. And you can do it like this by switching some of them off to zero and playing around with how strongly they can interact with each other. And once you have done that, you just keep away and you don't touch. You just let this thing settle into the ground state, and once it's done, you read out the result. And we are far from the first ones to have done something about this. We have definitely been standing on the shoulders of giants, in particular Daniel O'Malley across the pond. In his paper in the Scientific Reports in 2018, he describes how from the flow measurements in an X and Y direction in this particular two-dimensional medium with permeabilities in the X and Y, is able to invert back for those properties. What he does, though, is basically he describes a region of space where the flow is really good or really bad. So it's a very, very binary problem that he's trying to solve, but an excellent first application. He followed it up with a recent paper that was presented at the 2020 SDG conference, where he's trying to do a full waveform inversion using the same principle. There are countless caveats that have to do with this, but again, he defines two areas in a 2D subsurface. They either are very high velocity or very low velocity, in yellow or green. So those of you who are geologists are probably shaking your head right now and saying, this does not look like anything that I'm used to, and you'll be correct. But this is just a proof of principle of what are the little steps that I can do to sort of crack the case of what a quantum computer could do. So this was great inspiration as well. He does not solve the wave equation on a quantum computer. What he does is he uses a quantum computer to evaluate, not so much, so he's sort of calculating the local gradient to work towards the global optimum. He finds an instance of the model, finds the local optimum based on that iteration. He updates the model, solves the wave equation classically, and iterates. And so the quantum bit is only used for the optimization step. And this is yet another example by our friends and colleagues from Brazil, who have taken kinematic measurements of wave propagation in water and basically run a regression algorithm, if you like. They try to match the medium properties to the arrival times. Not too complex, but again, it's a nice exercise. So we thought, this is all really, really exciting. What is it that we could do about this that takes it one step further? And I really mean just a single step further. So don't expect, oh, we have now been able to affect the drilling decision. Far from it. But this is our first attempt at doing things. And again, what it took is a highly interdisciplinary team to really bring it together. So we have Diego, who understands the physics and the problem. We have Frank and Niels, who understand the quantum computer. We have a very talented and keen master student. We have Matthias, who really knows his optimizations. And I'm trying to make sure that maybe I'm a little bit of a glue in between all of those activities. And we tried small, and we wanted to see how big we can get. The idea behind the problem from a physical point of view is relatively simple. So in a desert environment on land, you will have areas, for example, such as wadis, right? So seasonal rivers. And those areas, you'll find that the wave travels through them differently, right? That the wave velocity in those areas is substantially slower than elsewhere. That's the picture in the middle. And what happens is that it creates, for the seismic signal measured at that location, it creates very subtle delays, which we call statics. So you can see the map of estimated statics on the right, and the aerial sort of representation on the left of what this wadi contours look like, and you can see that there is a sense of resemblance. So what does this signal look like? This is a signal that you would measure, and this is the signal that you would like to correct to, right? Those of you who work in seismic signal processing, you know that what we are looking for are hyperbolae, right? So this is a much more believable signal than this sort of slightly discontinued and contorted one. What you would then hope for is that it has an impact on your image, and it does, right? Those of you who are used to staring at seismic images immediately see that there is a greater focus in many areas here indicated with those arrows. You suddenly are able to perform some kind of interpretation, right? And all it took is to estimate those very small shifts in caused by local velocities and anomalies. And depending on the kind of algorithm that you're using to estimate those shifts, so you can see sort of statics that you can see in this picture, sometimes you can actually pick up such an amount of detail in those estimates that they actually start looking like an aerial photograph of the area. So how does this process work? You need to have an optimization principle behind it, and that's just stack power optimization. The idea is simple. If you add two traces which are misaligned with each other, then their energy is low. But if they are very well aligned, then their energy is high. You have fewer events, but they are much stronger events. You square it, you get the benefit from squaring a bigger number. And that's the mathematical description of it. Seems super simple and benign, yet it does fall into the class of complicated NP-hard problems. And if you're looking for what this potential energy objective function landscape look like, you're looking at it right now. All those local minima and maxima that you are just so welcome to get stuck in. And that's just for two traces with a possible, very simple ones that you just saw, with a possibility of shifting them by something in the order of 20 milliseconds relative to each other. So what Stam did so well is this part of the problem, where he found an encoding, how to move the geophysical problem onto, how do I map all the information from the geophysics onto the language of qubits? How do I then communicate this to a quantum computer? In a process, we had to introduce a constraint. So that's this, that's the lowercase p in the middle in the red square, because it turns out that we had to solve a constraint optimization problem. And then once you have that taken care of, you can send it to the quantum computer, and then the quantum computer comes up with some solutions for you. So you always start with a synthetic, and he just took a single trace, shifted it by a bunch of numbers left and right, and then tried to find a solution. And the quantum output was a perfect overlap, right? The problem was designed to make that happen. In the process, however, something interesting we discovered. We found that we are getting a lot of solutions. The problem was run about, I think, 500 or 1,000 times, and only a very small fraction of them actually satisfied the constraint that we imposed. And the constraint was very simple. We say, you're able to shift every single trace only once. So it's not allowed to, of the 16 traces, to shift 2 of them 16 times and leave the other ones untouched. That's the red area. Every single one being shifted once is the green area. And we saw that this, as a result, the quantum computer actually didn't perform very well. Found that only a very small number of occurrences was a very good physical solution. But with a small insight and a classical post-processing trick, we have changed it to that. So notice in the process, the vertical axis has changed fourfold vertically. We are now pretty much 99% of the time getting the global optimum for this problem. And every time we run this, it takes 2 microseconds. So it's not something that takes weeks. It's a very, very fast process too. So we thought, okay, let's challenge Stan a little bit, and then Diego figured out a small section of the steam arid model, and that's a model that's supposed to represent very well the sort of environment that you would find in the. And when you look at the numbers, you realize that this is a pretty big problem, because he got just 108 traces. And he tried shifting each and every one of them with 15 possible shifts. I think that with a sampling of something like 2 milliseconds or so. That gives you 10 to the power of 126 possible combinations. And in the spirit of scaring your audience in these sort of presentations with very large numbers, that's roughly the number of particles in the observable universe. Only once you multiply it once more by that number, right? And yes, these are excessively large numbers, and many people are using this to promote their methodologies. But this is the only methodology that actually uses quantum tunneling over thermal annealing. So it's pretty mind blowing. So this was the input, the traces that we have given him, and this is what he got using a deterministic classical solver, right? Because we want to see if we can do better than some classical tools. And he got an even better alignment using a quantum computer. And there's no attempt over here trying to benchmark anything, because it's still very much an ongoing area of research. But getting something on pretty much a first attempt that was at least on par was very encouraging. What I should stress also is that this was a hybrid solver, which brings me to my final slide, and that's the outlook. Because what we have learned during this project is that from this very simple initial idea of what it actually takes to run things on a quantum computer, much like you would find in areas such as data science, machine learning, etc., there's a whole lot of subject and domain-specific knowledge that is required, and then you combine it with your interdisciplinary team, and you find out that all of a sudden there's a lot that you can do. Depending on how you set up the problem before it becomes an IC model or after it becomes an IC model, that could actually have a significant impact on how big of an optimization problem you could fit on the quantum computer. Because it has 5,000 qubits, and it allows you to, for this particular problem, handle as much as something about like 100 variables. That's why we had 16 traces with 4 possible shifts before we needed to switch to hybrid to pack more in. You could split the problem up, and the way you split it up could also play a very important role on the quality of your optimization outcome. And as we showed you earlier on, if you apply, whether or not you apply some classical post-processing, you can make a whole lot more sense of the output of the quantum computer if you understand the underlying principles of how this quantum computer works when it actually gives you the answer. So as you can see, there's plenty of work for a geoscientist on just this very slide and for just this very simple problem. And yeah, I think the future is really exciting, and we're quite keen on seeing what else is out there. That brings me to the conclusion, and if you guys have any questions, I'll be happy to take them.
Thank you very much. Thank you, Matthias and Marcin. It was a very interesting presentation. I will ask, of course, to all the attendees to write in the chat an equation or to raise the digital hand so that we can unmute them for any question. And Florenza is also helping me with this. So Florenza, did you get any questions so far?
Not for now in the Q&A, and in the chat, just we have a comment from Hannes that says nice presentation.
Okay. Let's give some time to the audience. Maybe they have a question coming. So maybe in the meantime, I will, yeah, we got one.
I don't see it. Maybe they send it to you.
Yeah, it's privately to me, so let me read it. So it's from Huduma. He's saying first, thank you for a nice talk and congratulations on these results. Can you say a little bit more about how the Ising formulation was obtained for the residual statics example?
Yeah, it was relatively straightforward. All it took is maybe there's a couple of things that I didn't explain because I don't want to make it an overly mathematical talk. But what you can see over here. What you can see over here is the data that goes in. So what we needed to do is we needed to split this problem up into, again, classical sort of pre-computing and then quantum computing side of things. In the classical computing, we realized that if we are to substitute quantum-like variables that are understood by the quantum computer into the classical objective function, means that we would need to calculate correlations between individual traces for each and every single possible shift. And you could say, hey, but this sounds like a brute force approach, which will run away from you the moment you have just a very large number of traces. But the point over here is that we only do it for pairwise interactions. So we only see how one trace is talking to another trace, and then how trace 1 is doing with trace 2, 2 with trace 3, but never more than a 3-point interaction, so to speak, which is equivalent effectively to determining calculating what is the thickness of the bar over here. So to calculate the thickness of the bar, we needed to do the classical computation. And that was it.
Let me unmute Hubert to see if he has other questions.
That was okay. Thank you very much.
Good. Florencia, we have other questions, right?
We have another question from Malcolm Francis. He says, this reminds me of the early fluid modeling machines that allow you to set up a grid of resistances and then measure voltage through the system. I don't know if you have any comments regarding that.
Yeah, I mean, effectively, if I understand you correctly, it's an attempt of trying to actually map a way of trying to optimizing a problem onto an actual physical system that self-optimizes, right? And in a way, it's very similar, except for one detail that, where are we here on this slide? Those fluid flow machines do not quantum tunnel. And that's what makes a big difference on the highest of all possible levels.
And Malcolm, you're unmuted if you want to further discuss.
Well, I guess maybe.
Try again. Can you hear me now?
Yes,
yes.
yes, we can hear you.
Sorry. Yeah, I thought I had to unmute myself and you'd already done it.
I did it
Yes,
for you, sorry.
what I'm getting at is in the case of these early machines, I remember one in college where it was an entire grid of little pots. You set up your model on the pots and then that, the equivalent of the fluid flow was actually the voltages running through it. So you could then sort of tap out at both ends. And I think also the government had a method of modeling the economy by flowing water through a series of tanks and valves. So what gives us the problem here is understanding this tunneling. In other words, what is that in terms of how do you then map a real problem into something that you don't understand?
Okay. So the bottom line really is that you're trying to so the working of the quantum computer itself is pretty well understood of this particular quantum computer. So how things tunnel, why they do, at what time scales. This is all things that that is understood. In principle, you just have a physical system that is allowed to make that happen. When you're looking at the mapping of the problem that you have onto a problem that is native to a quantum computer, what you effectively want is just an energy landscape. So the fact that you can associate a certain solution to a certain amount of energy, and that's all there is to it.
Yes, I think that was what was happening in this grid of resistances. In other words, if the voltage was higher in one part of the system, it would automatically flow into a place where it was lower. Mm-hmm. And then at the end, you just had to pick off the voltages on a grid or whatever that represented your solution. Whereas here, you're saying it's looking for that minimum energy level on your graph that you're showing there. And so any time it can leak to a lower point is a sort of equivalent to the voltage leaking to in other words, the current drives electrons down into the lowest voltage part of the system until that's filled up.
Yes, so, but imagine that you can, on the same run, carry out all possible combinations of initial voltage or current distributions in that machine, such that at the end of the day, through interference, much like when the waves constructively and destructively interfere, through interference, it will really, at the end of this flow, collapse to one of the leading possible least energy flows. So you can start your system in a superposition of all possible representations or well, configurations. But at the end of the calculation, it's the ones with lowest energy that will show up with the highest probability. So that's not something that you can accomplish with a classical current. And here you can do that because the physical nature of this is superconductor, is quantum. Because, well, actually the niobium qubits that are used by this particular quantum computer rely on superposition of superconducting currents happening at the same time.
Maybe, Marcin, could you go back to the formula? Slide with the formula.
I think it's here, right?
Yeah, so maybe, well, if you go one step back, then these boxes aren't there. Yeah, okay, yeah, this one. So maybe this can be easier understood as what we have, these two di, dj. These are all the combinations, yeah? So this, what is it, quadruple sum over the i's, the j's, that is all the, let's say, the pre-computed data, yeah? And then the x's are a kind of selection process, yeah? So do we take this one, let's say, I is 1, j is 2, tau A is something, tau B is something. Do we take this combination or another combination or yet another combination, and to make sure that we are not taking multiple combinations, yeah? So the multiple that correspond to the same, there is this other term. So on the very right, we are kind of penalizing whenever we have, yeah, say if we are selecting something twice. So maybe you can see this as a kind of, yeah, combinatorial selection problem, where you're offering all the possibilities to the quantum computer and make sure by this constraining term that the computer is not giving you an invalid. So invalid would mean you're moving it up by 1 and up and down by 2. Yeah, so you have to make the choice. I either move it up or I move it down.
Yeah.
Okay. I guess we can pass to the other question because there are a few coming, and we passed a 6 actually. So let's try to go through some other questions.
Yes, we have another question from Case Papener. He says, Marcin, your specialty is multiple elimination. Have you thought how to use quantum computing for this problem?
Yes, thank you, Case, for ratting me out that I'm imposter here on quantum now. Just kidding. But yes, we have had some very early conversations at the end of last year, because it is a problem that is very close to my heart, but we haven't gotten anywhere just yet. We're looking for something relatively simple first. And this was the simplest yet complicated enough that we could find. But we'll keep looking.
Thank you so much. We have another question from Hannes. He asks, what is your way forward for your work group? I guess like future of the research, he means.
So Matthias, do you want to start, and then I say how things are from our end as well?
Yeah, sure, I can start. So I should say here in Delft, we are looking at both. Yeah, so at the moment very imperfect universal quantum computers and also on the quantum annealers. The way forward for me, from my work group, is on the D-wave side or on the quantum annealer side to look at which type of problems are mappable to this Ising formulation. So it's basically the last slide that Marcin was showing, what interesting problems can be mapped into this formalism, yeah, and then how to implement them, how to solve them, and how good can we solve that, and can we push the D-wave machine or this quantum annealing approach to the limit. And on the other, so less mature side, we are also looking at a completely different field. Can we use these universal quantum computers to do something that we are nowadays doing on classical computers? Yeah, differential equations, solving linear systems. There is also a lot in this field, but that is not near, not midterm, that is really long term. Yeah, so these are the two research fields we are looking at in my group. Maybe Marcin, you want to continue?
Thank you. No, so we've been very closely monitoring these activities in Delft and outside of Delft for now a couple of years, and we feel like we are in a position to start stepping in with sort of very modest time investment, but still, you know, this is the time to get your hands dirty. Step one will be follow Stan's footsteps and now see what impact it will have on an image. I mean, how exciting would it be to be able to squeeze in a quantum computer somewhere in the processing workflow and find out, has it made a difference in the end, yes or no? There are a number of things over here that we haven't discussed, which have to do with bandwidth and sampling, and all these things actually have an impact on the objective function. These are things that we would like to learn, and work with, you know, with excellent researchers like Matthias, but also there's a number of other people in Delft that we've been in contact with. To try a number of other simple toy problems in the coming year or two. So that's one. That's on the optimization side of things. I should circle back actually to what Case asked, because I have written a paper, a conference abstract on how you can use certain quantum algorithms to solve a Gelfand-Levitan Marchenko equation, and how, as far as the inverse scattering or inverse problems in geosciences, that by complete coincidence is kind of fits the quantum description of things, simply because you're, without getting into excessive amount of detail, on a quantum computer, when you have a superposition of things, you try to measure what it is and you always get just one answer. So it's like looking at a big problem through a through that's behind the door, and all you have is the keyhole to look at it. And a Gelfand-Levitan Marchenko equation is very much like it, where you solve a big inverse problem, and then you discard the entire solution except for one value in it. And there are a lot of interesting parallels in there. So perhaps we will continue some of this more theoretical work as well on the side. Let's see.
Next question.
Yes, thank you for your answers. Yes, next question is from Venkateshwaran Bhaskaran. He says, "Hi sir, which programming language do you prefer?"
Well, I think that's not so much which we prefer, but also which one has to use. Yeah. So in the quantum world, Python seems to be the number one language. And then, say for D-Wave, you have to use the Leap SDK offered by D-Wave. Yeah. So you have to use this one, let's say Python package or Python extension to bring your code or to bring your problem to the D-Wave machine. If you would look at other quantum computers from other companies, they have their own SDKs. Yeah, so it's really in a very early Wild West state. So every computer has its own language, or well, let's say Python package that you have to use, and then you sometimes can convert from the one to the other. But it's not so much a question of what we prefer, but what we have to use if we want to use a computer A or B.
No, I completely agree here with Matthias. It will be the programming language that somebody else will make me use. I think it's just the simplest way to put it. I would just say what's more important is to understand what happens. Because coding something up and then feeding it a bit of data and getting a solution out of it is not enough. So if you're looking for where to invest your time study-wise, try first get the bigger picture. Worry about the programming language later.
Thank you. Next question.
Yes, we have another question from Yap Mont. He says, do I understand that for different kind of problems, different hardware setups is needed, or is there a general setup that can solve any problem?
That's an excellent question. In principle, the answer is both. I'm not sure if you like the answer, but I think it really. So there are a couple of things. On the universal quantum computer, the ones with all those complicated gates that Matthias showed you, right? If you want to run this, there are countless benefits to be had on the architecture side of things. So it might happen that different chip design, different connectivity between different qubits will have a massive impact on what you are or are not able to do. So the recent development that you could see from IBM, where they decided to actually sacrifice connectivity between qubits to be able to have more qubits. These are indeed the steps that are being made in that direction. When it comes to the quantum annealer, here we have a very specific task, and that's optimization. And we're combining this with the fact that all optimization problems are somewhat alike, and as a result, you just want to find the biggest machine that can squeeze the largest optimization problem for you to solve in a way that a quantum annealer does. And the rest is not that important.
Maybe if I can add, because I understand the question, is it, say, would there be a reorganization of the hardware needed? So do you really have to move around hardware pieces in order to solve problem A or B? There are, so this nice figure where there was a hardware realization, that was really a kind of manufactured for the problem. But normally these programmable, and this applies to both, to the universal and to the D-Wave, these programmable, software programmable quantum computers, the hardware is kind of given to you as a black box, and with some code, you can exploit this hardware as it is, as good as possible. Yeah, but you do not have to, let's say, rewire, technically said, the hardware.
That's correct. Yes. No. So I completely agree here, Matthias. What I was thinking one step ahead of this is that given a fixed number of qubits, suppose you have 100 qubits and you want to make the most out of it, then depending on how you connect them for a problem that you're trying to solve, that will have an impact. But most likely, you will never be given a chance to do that because the amount of engineering, quantum engineering in the process might be very prohibitive. To be able to both work on the software side and on the hardware side. Yeah, it's a highly interdisciplinary field where it really takes a lot of people to come together to do something useful.
Great. I think we have 2 more questions in the chat, so let's try to address them too.
Yes, we have the next question from Hoop. He asked, quantum annealing, in my understanding, works for non-linear inverse problems where you have one clear global minimum. For geophysical inverse problems, there is typically a substantial null space. Am I correct in understanding you would need a general purpose quantum computer for that?
You broke up a little bit when you were in the second part of the sentence. Would you mind repeating that, please?
Yes, I'm sorry.
Okay.
Quantum annealing, in my understanding, works for nonlinear inverse problems where you have one clear global minimum. For geophysical inverse problems, there is typically a substantial null space. Am I correct in understanding you will need a general purpose quantum computer for that? Was that clear?
Yeah, I'm quiet because I'm thinking. Matthias, do you have any immediate thoughts or comments on this?
An immediate thought would be, why would a general purpose quantum computer overcome this problem? Yeah, so if there is not a global minimum, but multiple ones, I don't see how a general purpose quantum computer would kind of magically fill that gap.
No.
So I would say you can also attack this problem with a quantum annealer, but you should be aware that because there is not a global minimum, that you will run it multiple times and you will get multiple good solutions. Or yeah,
that's why we have those backup slides.
Yeah.
So if you because I think what Hood was asking about is indeed a math problem rather than a how do I get to a solution, a compute problem, right? But maybe this will shed a little bit more light on this is a couple of screen grabs that I took.
Maybe do we want to ask Hood to unmute himself and clarify a bit the question?
Let's do it.
Yeah.
So yeah, sorry.
Okay.
Now
Yes.
you should talk.
Okay. Hi. Yes, it's basically like Matthias was saying. You would want to find all possible global minima, if you like, that are equally possible to be the answer. And my understanding is with the quantum annealer, you land in one global minimum, which is fantastic already. But I was just thinking if you would want to know the ensemble of models that all fit the data.
Okay, now I understand this a little bit better. So if you have several global minima that they are exactly at the same energy level, then these kind of histograms that I showed you earlier will tell you exactly that. We repeat this process also many, many times, and then you end up with an energy distribution like this green bar over here. And behind that, there is a register of qubits, which basically tell you what the solution is. So all this picture tells you is that we hit a global minimum each and every single time. However, if they are different global minima, all of them will be here. Because if you're in a superposition of two global minima, the moment you're going to measure your qubit register, you will force the wave function of this quantum computer to collapse to either one of them. And with the same probability, you're gonna find out exactly which each and every one of them is. So yes, right. You'll get all the global optimum.
But geophysical inverse theory always have a certain level of misfit, right? So there's always a range of minimum that you allow.
Yeah. So you can do the same thing over here and basically say, okay, how about I'm interested in studying, for example, this section of this energy histogram, and I pass it on to in my workflow and understand and try to do uncertainty analysis, stability, or whatever, right? Yeah. So all this does is basically instead of getting trapped somewhere here consistently and not even knowing that you are stuck in a local minimum. Of course, there are ways of finding out, right? But it basically tells you with much greater certainty that yes, you are actually sitting somewhere in the lowest energy level. Mind you, we are just scratching surfaces over here, right? These are small problems on a very simple thing. So I might be, talking back this point in a couple of months or years if we find a counterexample. It's we'll see.
Thank you. I guess we have to take the last question because we are a little bit late on the schedule.
Yes, we have a last question from Hannes. He says, could you not apply this on a larger data set, just overlapping window by window?
Yes, you could. So that indeed brings me so very short to this part when we talked about problem segmentation. So how do I split up my big problems in chunks that can be fed into a quantum computer? This hybrid solver that we talked about for the ARID model does exactly that. The problem is that it is a stupid solver that is super generic and it's supposed to work for applications from logistics network optimization, through finance, material science, what have you. And if you find a clever way of doing this for your geophysical problem, then you could. It's just it takes some elbow grease and be a bit clever. Maybe to illustrate this a little bit better, this is a nice picture which basically shows you the complexity of the problem that you could solve on a quantum computer as a function of time and the generations of different quantum computers. And what this big ball here represents is that if I have that 5,000 qubit computer that is called quantum advantage, is that you could squeeze in a problem of fully connected 100 variables. And when I showed you this example of 16 traces with 4 possible shifts, that's exactly 96 possible variables. And so that covers roughly most of that sphere. The moment you want to do something bigger than that, you have to start segmenting, you have to start implementing all kinds of clever hybrid tricks. I hope that answers your question, and maybe with some bonus on top.
Thank you, Marcin. So I guess we can close here the Q&A. I want to thank again the speakers for the presentations, for the discussion. And I will close with the last 2 slides with some announcements about the next events. So let me share my screen again and go in presentation mode. So yes, the first thing I want to announce is the next month event. It will happen on March 18th. And it was organized by Yuri Brackenhoff. It's about DAS, fiber optic seismology in volcanic glaciers and other challenging environments by Professor Andreas Fichtner from ETH at Zurich. So please write down in your agenda. This will be next month. And finally, as usual, all the acknowledgements for this event. First place, Professor Matthias Möller and Dr. Marcin Dukalski for the presentations, Aramco Versi for providing the WebEx event platform, all our friends from the different EAGE local chapters, and the student chapters as well. And with this, I will close this meeting. Thank you all for your attention, and see you soon next month.
Thank you, Diego.
Bye-bye.
Thank you.
Bye, everyone.